Origin of irrational numbers. Until Pythagoreans, it was believed that all numbers are rational and hence can be expressed as ratio of two integers. But Hippasus of Meropontum, who lived through 5th century BC, discovered that under root 2 cannot be expressed as ratio of two integers. If it was, so let's prove that in modern day mathematics we could be asked to prove that under root 2 is not a rational number. Prove that under root 2 is not rational. If under root 2 is rational, if it is, then it must follow the definition of rational number. And what is the definition of rational number? That every rational number can be expressed in the form of p over q, where p, q are integers and q is not equal to 0. If under root 2 is rational, then obviously under root 2 can be written in the form p over q, where p, q are integers and q is not equal to 0. But here we further assume p, q are in lowest form. Lowest form means that there is nothing common between p and q. Like they are in the least form, in the simplest form. P and q, they do not have anything in common other than 1. If so, then obviously we can write p is equal to under root 2 q by bringing q on the other side. And if we take square on both sides, then what follows is that p square is equal to 2q square. Let's call this as equation 1. Here, if we carefully take a look on equation 1, it means that p square is even, because any number that has 2 as one of its factor is called even number, which means p square is even. And if p square is even, then p itself is even, because p square is a complete square, and any even number complete square could only be so if p itself is even, which means p square is even, so p is even. For example, take a look on 16. 16 is a complete square and it's even. Its square root 4. 4 is also even. Similarly, if you look at 64, if it's a complete square and it's even, its square root 8 is also even. So, if p is even, then p is equal to 2m for some m belonging to I, because a number could only be called even if it's multiple of 2. So now substituting, if we substitute this equation, this value of p in equation 1, substitute this value of p in equation 1, which means 2m whole square is equal to 2q square. And now we can clearly see that this gives us 4m square is equal to 2q square, means q square is equal to 2m square. Again, what does this prove? This proves that q square is even. Again, this proves that q square is even because it's multiple of 2, and hence Q must be even. Because if its Q square is a complete square and it is even, for the reason we have described before, Q is again even. If so, then what does this means? Q is equal to 2n for some n belonging to I. But doesn't this contradict our basic assumption? If Q is even, wait a minute, we also know that P is even. Then if P and Q are both even, then 2 certainly is a common factor, which contradicts to our original assumption that P and Q are in lowest form. This is a contradiction, and if it is contradiction, this means that our basic assumption was wrong. And what was the basic assumption? That under root 2 can be written in the form of P over Q. This means that under root 2 cannot be written in the form P over Q, where PQ belongs to P belongs to I, Q belongs to I, and Q is not equal to 0. So under root 2 is not rational number.